Now I would like to go into simple linear regression as the statistical model that we are going to be talking about. So remember the previous chapter was numbered as 0, in which I talked about statistical models versus mechanistic models or modeling. And when it comes to statistical models, I said that it is actually the aim of trying to find a relation between what we may call a quality variable in process engineering or dependent variable in statistics, and with the process variables or independent variables or covariance predictors, depending on the research area. Usually a slightly different terminology may be used. Anyway, so and the relation will be confined to a linear relation in terms of the parameters here. So we are not going to be dealing with a, for instance, a linear regression model such as this one, right? Because it's going to be non-linear with respect to parameters, and we are going to be concentrating on a single regressor. So we are not going to have an x2 here. And due to the very same reason, we are not going to have an x square here also. Beta 2 times x square element. Actually, you can easily say that, okay, this is the same regressor. But still, the way that this approach in linear regression, especially in the least square solution, is to assign a different variable to that squared original variable term. I'm not going to go into that detail. So that's why these are not included simple linear regression. So the model that I'm going to be interested in, and the phrase is going to be population regression model, will be represented by this equation, where simple corresponds to the single variable, single predictor case, and linear correspond to linear with respect to parameters. So now let's now from the we're going into a more focused area. In the previous lecture, I talked about a general view of statistical models. Now I'm going to be talking or emphasizing the view from linear regression perspective. So from the linear regression perspective, this y is going to be our dependent or our response variable, where beta 0 and beta 1 are going to be our regression parameters. They are going to be, note that they are going to be population parameters, which are need to be estimated. And we are going to have an independent or regressor variable x, and we are going to have a random error term, which is actually, which makes this whole model a statistical model due to the stochastic or statistical nature of the random error term. And we are going to be assuming that error is normal distributed with zero mean and sigma square variance. Now, one important point here, in the previous lecture about statistical models, I said at the beginning, I assumed at the beginning that x itself also is a random variable. But at some point, I said that when it comes to linear regression, we are going to be taken for the case that x is going to be taken as a constant value. So that may actually cause some confusion. So let me put it that way. Through the linear regression, we are going to be always taking x as a constant value. This is not a random variable. What do I mean by a constant value? In terms of engineering or process engineering, it's easier to understand. A person in charge of a process or equipment comes, and he or she adjusts a specific value to a certain input variable. So once that input variable is specified to a certain value, this mechanism related with the natural laws somehow in a way that's not apparent here, but that's the nature of statistical laws. We do not usually take into the phenomenological or equations, constitutive equations, or we don't take into fundamental laws. But of course, there is also we assume that those fundamental laws are still running in the background. So somehow the relation, the constraint between y and x is through those fundamental laws actually. But from an epistemic point of view, that's not what we are trying to searching for, or we are trying to determine. We are just trying to determine the relation between x and y. Anyway, once x is determined to a specific value, through these beta 0 and beta 1, which are again assumed to be constant. There's a deterministic contribution of that constant input value variable to the output value, but the output value will not be only consisting of that deterministic, that single value part. Each time we measure y at the single input value, each time we measure the output value, we are going to be obtaining a slightly or maybe a vastly different value due to the random error, and it is the magnitude of its variance. So that's basically the perspective that we are going to follow. X is going to be a fixed variable, not a random variable. It's going to be specified by the user. But fixed variable does not mean that, note that it's not going to be like a parameter. So parameter is a constant, also a fixed value, a fixed variable is also a constant, but there's a difference between parameter and fixed value. This fixed value for each experiment may be specified to a single value by the user, whereas beta 0 and beta 1 are constant, determined through natural laws. That's what we are trying to estimate. Anyway, so what we are going to do, the perspective that we are going to be using is, once x is determined here, so it means we are at a specific x value here. And note that this is scatter plot of y and x values. What do I mean by scatter plot? Each observation here includes a couple of x and y values sampled from a set of experiments. Anyway, actually, we assume that a real relation, a true relation between y and x exists in the form of this straight line. So this is going to be basically, this straight line is going to be equal to expected value of y given any x value. Why this is the case is very obvious, but I'll come to that in a minute. So given some x value here, the corresponding value, the projection of that x value on this line, so the corresponding value on the y-axis will basically be equal to, given that x value, what is the expected response value. So you are running your process. Think about the distillation column. Let's say we have some feed entering the distillation column. So we let the feed at a constant level. At that constant level, and everything else should also be as constant as it can be, except the uncontrollable nuisance factors, I may say. So in this case, what is going to be the expected value of the quality variable? Let that quality variable be, usually it is the distillate composition. So each time you are going to be observing a y value distillate composition, each time you sample at the same xi value, note that you are not going to be on this line. You are going to be here, along this vertical line, because you are running your process at that corresponding xi value. So we are going to be obtaining samples here on this y values, but around this expected value. And note that the distribution of these samples will be normal here on the where the median or the mode or the expected value is here, just the peak, and this variance here is going to be exactly equal to that. And this is something I talked about at the end of the previous lecture, but from the linear regression point of view, what we have is this one. Let's actually just do these very simple relations. When you take this y and take the expected value of both sides, right? Since these are constant, beta 0 and beta 1 constant parameters, and x is a constant variable value for that specific run, for any specific run, you can take this as expected value of random error is equal to 0. So the expected value of y given xi is actually this point here. So these are going to be given any xi value. Let's say x1 is here, x2 is here. So for given any x value, the corresponding expected values for y is going to be the projection of this line to y-axis. And the variance of y given xi, and what does variance here actually? Note that this is going to be the expected value. It doesn't mean that each individual observation will be here. It's just like a normal distribution here, and we randomly draw samples from this normal distribution. As long as xi is, for instance, at that value, we are going to be taking samples from this specific distribution, where note that actually this corresponds to now y-axis. That's why I plotted here. So you can safely forget about this part. Now we have a distribution here, y-axis, so you can easily rotate it that way if you still find it difficult to visualize. This is what we have here. Given, so this point here is going to be exactly here, right? The peak point. This point here is going to be expected value of y given xi. And around that value, the width of the single values that we are going to be obtaining will be proportional to the standard deviation of that distribution. And that standard deviation is actually standard deviation of the random error terms. If the random error terms has zero standard deviation, we have a purely deterministic process. Every time we apply an independent variable of xi, this is going to be exactly the value that we are going to be obtaining. Therefore, the test results will be exactly on this line. These are going to be the individual values. But when variance is of the random error is non-zero, then still this is going to be the expected value, which means if you run the experiment many times for different xi values, this is going to be the average y values that you are going to be obtaining. But once you repeat the experiment at xi, you are going to be around this range. And if the variance is higher than this variance here, the width of the distribution and the possible xi values, let's say this is second set of xi values in circles, they are going to be in a more broader range. If sigma square even more increases, now let's use some diamond shapes here, this is going to be even a more broader distribution. So this is going to be a noise level. And as I said previously, this may correspond to process disturbances or either measurement errors. So in observing the y value, these quality variables are usually result of laboratory analysis, whereas these x values, when it comes to process engineering, these are usually process variables which are determined online by automatic or electronic equipment. So therefore, it is quite possible that there is going to be a large error or significant error due to, because we conduct some tests to determine this y value in laboratory. So therefore, this sigma square may be a pretty much high value. Now another point. Now you may say that what about the error in x in regressor variable? From this perspective, where we use the x to be a constant value determined by the user, we assume that x is free of error. So the whole error is on y. So the whole that's why x is assumed to be a deterministic variable. If we assume that there is random error here, or measurement error, or any error noise on x, then x would also have turned out to be a random variable, but that's not the analyze that we are going to be using here. Anyway, so now, actually, once I talked about, let me go back here. This is what we call population model. This is just like a model such as this one, as I talked about previously. That was basically, this is the model that, although I haven't shown you explicitly in the whole second part of the course, this was actually the model that we use maybe without thinking about that. Y is normal distributed, actually error is normal distributed, it's 0 sigma squared. That's a more formal approach. Now, okay, this was the model. And using this model, I have already shown you that the y also turns out to be normal distributed with population mean mu and sigma square variance. So for this case, although I haven't shown you the model by this way, we talked about how to estimate mu and sigma square. So we use some methods, right? And we come up with estimates of mu and sigma square. And actually, the point estimators that we use, the most efficient ones under normal distribution, I said that x bar is the minimum variance unbiased estimator for mu. So this is used, and we use s square for estimating sigma square population value. population variance. And note that S square was the factor 1 over n minus 1 was there, right? Due to the loss of 1 degrees of freedom. But that was an unbiased estimator for sigma square. Expected value of S square is equal to variance. So what we do is, once we assume a model of this kind, or actually we assumed a model of this kind during the covering of these in these lectures, but actually you may also transform it into a model like this. We have taken a sample of Y observations, and from those samples we come up with X bar and S square values, and we use these as point estimators or point estimates, and also use them to construct confidence intervals for hypothesis test, everything else. So we are going to follow exactly the same procedure. The parameters here are beta 0, beta 1, and they are constant, and sigma square, 3 parameters here. So now by taking a sample, but now the sample will consist of xi and yi values, we are going to be estimating these parameters. But just like how did we estimated population mean and variance value, we use some estimators, and I said that these are the best estimators, and best here corresponds to minimum unbiased minimum variance unbiased estimator for Gaussian distributed random variables. And then actually I show you a method which is called max to find the maximum likelihood estimators. Anyway, we have a similar approach here, and the similar approach will be as follows. Now, what we call is a sample regression model. Is the only change is we use a subscripted version of the population regression model. This is the general model here. Actually, maybe that would be a better idea if I have used here capital letters. Whereas here now we are talking about sample values. So this sample will be collected from the experiment. Now what we do is this, and remember what are we doing right now? What's the aim here? To determine estimates for beta 0, beta 1, and variance of random error. So we would like to determine the population parameter, or now, in other words, model parameters. We would like to obtain efficient estimates of them. So what we do is this. Now, yi and xi values are known for each experiment. So what we do is we leave this error term on one side and these two terms on this side. So ei is going to be equal to yi beta 0, beta 1 xi. This is also a minus sign. Note that now we know these values from each experiment. So from I1 to n, for each observation, we have yi and xi values. What we do not know are beta 0, beta 1, and of course, we don't know the error terms. So what we do here is this. We take the square of each of these terms and sum them. So this actually ei square means square it and sum for n of these values and call this n. So this is what we call sum of squares. Of errors. Now, if we had really, or before and somehow know the true values of beta 0 and beta 1, that would give me sum of square of error terms, right? These are, each of these terms would be the error itself, random error, then square them, sum them is sum of square. It's just the definition. Now, the method suggested by Gauss is like this. We would like to estimate beta 0 and beta values such that this summation is going to be minimized. So we would like to obtain a squared, a sum of squared of error terms to be minimized by optimizing beta 0 and beta 1 values. So what is the intuition behind that? The intuition is something like this, actually shown here. Let me just go over it. Let's say that these are the points here. Forget about E1, E2, all these things. Here, these are the points that we obtain at the end of an experiment. If I tell you to draw a line which seems to fit to those points, this is probably what we are going to come up with. This is not what you are going to come up with. This is not quite possibly what you are going to come up with. This is the line that you are going to be come up. Of course, it may change a little bit. So the question is, what is so special about this line? Or in your mind, what do you do so that you draw this line that seems to fit to those points? So what we heuristically do is, we would like to draw a line such that for the x value here, the corresponding y value on this line and the actual y value here, this error is as small as possible. This is quite possibly that's what our mind heuristically does. So, but note that this is a vague definition. Minimizing the error terms is not exactly equivalent to minimizing the sum of square of errors. So what do I mean by that? First of all, here we have a squaring thing here. Well, I said that in a heuristic case, there is no squaring here. It's just sum of squares. So it seems that we are trying to minimize something like this, the absolute value of errors. And that's interesting because actually there is a regression technique which is called least absolute errors, LAE, which exactly use this objective function. So least absolute error regression defines an objective function, a cost function like this, and tries to minimize this value by optimizing beta 0 and beta 1 values. But this is not a very friendly function, absolute value, because the idea is the absolute value function, if I draw it, for instance, for different I values, this is going to be the function itself. Right? One. So what's wrong with this function? Now I'm talking about minimizing. I guess you have seen in your previous mathematics course, minimizing a function which are going to consist of at least two variables here is going to be connected or is going to be actualized by taking partial derivatives and equating them to zero and solving these unknowns. And that's exactly what we are going to do. Therefore, we should be able to take the partial derivatives. Therefore, this function should be differentiable. Now, the problem of this function is at this point, it's not differentiable because as you can see, the limit from the left-hand side and the derivative from the left-hand side and the derivative from the right-hand side here are not equal to each other. Here we are going to have a plus 1 derivative here. So it's going to be the E in absolute value over the E is going to be equal to, well, let's not call it E to make this a continuous function, right? So this is more realistic. Now E is, so this is going to be equal to plus 1 if E goes to 0 from positive direction, but limit E goes to 0 from negative direction. If you go the E over the E is going to be equal to minus 1. Since these two are not equal to each other, this is not a differentiable function. Since this is not a differentiable function, but trying to find the minimum of this function by differentiating, by partial differentiation, will not work. So there are some modern methods to dealing with this least absolute error regression, I may say, but of course we are not going to go into this. We are going to follow the procedure of Gauss, which is instead of this absolute value, we can do a similar thing. Now, since what absolute value does is we don't, so let's first about think about why don't we use this one to minimize this value, because the positive and negative error terms will cancel each other, and this is going to be actually going to be equal to 0, right? And actually I can easily show that the least square line here is going to give this equation to be equal to 0 here. So instead of that, absolute value is used, and a similar approach may be squaring this value. When you do that, it has the same function, at least in terms of making the negative values positive, similar to absolute value, but it has another function here. It makes the large errors even greater. What do I mean by that? If we have an error term, let's say minus 0.5, when you square it, it's going to be 0.25. That minus 0.5 absolute value of 0.5 even has been decreased. But if you have an error of, let's say, 3, then this error squared is going to be equal to 9. So the large error will be heavily penalized. But that's not a deficiency. Actually, as Gauss has shown, this objective function, defining that way and minimizing the objective function, is actually ideal, or gives the minimum variance unbiased estimator for Gaussian distributed random error terms. So that may seem interesting, but also this is this solution that to this problem seem to be a kind of escaping from the difficult question. But when it comes to Gaussian distribution, this objective function is the ideal one, I may say. Anyway, so how are we going to minimize this? As I said, we are going to take the partial derivatives and equate to 0. So what do I mean by that? The idea is very simple, son. Now L is equal to this expression, but let's remember what we know here in this expression. We have a couple of observations. So let's say we have 3 observations. So what we know here is y1 value minus beta 0 minus beta 1 x1 square. We know this value and this value, plus y2 minus beta 0 minus beta 1 x2 square, plus y3 minus beta 0 minus beta 1 x2 x3 square. So what we know are these encircled predictor and response variable values. We are going to conduct an experiment, right? 3 experiments here. So these 3 experiment results are going to be x and y values, and using those values, we obtain this L value. So what we need to find is minimize this L. Here the parameters are beta 0 and beta 1. And actually now, starting from this point, there is going to be an important, let me not say trick, but something that you should consider it. Now, this equation, when given that way, is actually for the real beta 0 and beta 1 values. Now, at this point, however, when I say I do not know these beta 1 values, right, I'm going to give different values to them and minimize this. Now, these turn into hat, or these are turned into estimates. And now another, actually an important, maybe not that much important for this level, but actually an important point, what we are actually minimizing here when we give different values for beta 0 and beta 1 are not error values anymore. They are going to be estimates of errors. I'm going to talk about this. So this notation is actually, this whole notation is not very much rigorous, I may say, but that's okay for our purposes. Anyway, so what we do is we take the partial derivative with respect to beta 0 and beta 1. And that's how we show it. Take the partial derivative with respect to beta 0, and at which values they are going to be beta 0 hat and beta 1 hat. These are going to be least square estimates. So let me do it properly again. This is yi minus beta 0 minus beta 1 xi square. This function, I'm going to take the partial derivative with respect to beta 0, and I'm going to evaluate the partial derivative taken form at the beta 0 hat and beta 1 hat values. To be more specific, you should write here least square also as a subscript, or in any other notation that you like, but you usually skip that. And this is going to be equal to 0. Why? Because if these are the extremum values, or these give the extremum values, or minimum value for L, therefore the partial derivative with respect to each of these parameters should be equal to 0. So now the point is find the partial derivative with respect to 0. This is a summation sign, but since these are linear operators, you can change the order of them. So it's going to be I from 1 to n, beta 0 by I minus beta 0 minus beta 1 xi squared. Now, when you take the derivative with respect to, and this is going to be equal to 0. And when you take derivative with respect to beta 0, it's going to be equal to 2 times yi minus beta 0 minus beta 1 xi. There's going to be also a minus 2 here, but because we have also minus 1 here. But that minus 2 is going to be taken outside, and since this is equal to 0, this minus 2 is not going to have any contribution here. Therefore, what we are going to obtain is, here, this is going to be simply equal to yi. Now, actually, this term here, right? And I can now apply summation to each of these terms, and I can take these terms to the right-hand side. It's going to be beta 0 plus beta 1 hat xi. Now note that magically beta 0 and beta 1 turned out to be, or were converted, transformed to their estimates. Where did that happen? Once you apply this derivative and equate to 0, here it's at this step, then now we are using these specific values. These are the least square solutions for beta 0 and beta 1. Note that you can feed any value here, but we use specifically these values, but we don't know what these specific values are. So anyway, so this from 1 to n. So this is again 1 to n yi is equal to, now beta 0. I do it step by step, so for that, for those who are not very comfortable with the summation sign can easily follow. So we have n of these beta 0 constant terms. So this is going to be n times beta 0. Now when we have constant again beta 1, take it out, beta 1 xi from I1 to n. Now note that in mathematics courses, you are usually accustomed to finding solutions. Usually x are unknown. You try to find them. That's not the case here. I repeat again, x and y values are given to you. From those x and y values, for instance, this says that sum all the y values. It's this one. And this actually is going to be sum all the x values. So basically, this is going to be a scalar here is equal to n is the number of observations, some multiple times beta 0 plus beta 1 times another multiple. So this is going to be the first equation that we have. Note that we have two unknowns here. And we do the very same thing for beta 1. This time, I'm not going to go into the same procedure, but one thing that you should consider is when you take the partial derivative of beta 1 here, right, there is going to be a minus x1 term. Be careful about that. So let me put it that way. Now, let me write it here. This time, again, I write it inside the summation. It is beta 1 yi minus beta 0 minus beta 1 xi squared. When you take the partial derivative with respect to beta 1, this is going to be again 2 is here, 2 times. This time, beta 1 also has also a coefficient of minus xi. Let's get rid of this, put it here, times yi minus beta 0 minus beta 1 xi squared. This is going to be equal to 0. Again, that minus 2 can be taken out. It doesn't have any effect. So this is going to be actually equal to, note that it's going to be xi times yi is equal to, oh, there is no square here, of course, is going to be equal to, let's see, beta 0 xi plus beta 1, again in summation, xi squared. And then we take beta 0 out. Here it's going to be beta 0 plus a summation of xi. Again, we can find these values. When it comes to this one, it means that since xi and yi values are tabulated like those, we are going to multiply for the first experiment x1 and y1 value and come up with xi and yi value here for the first experiment. Then the second experiment, third experiment. For n experiments, you sum all of these. This is going to be the corresponding scalar here. And for this last one, this is again going to be where there is, you can take this beta 1 out. So this is going to be equal to xi squared. Here, xi squared simply means take each of these experiments, square them, right? This value, this value, this value, and add all of these values. This is going to be xi squared. So again, this is going to be scalar, scalar. I'm sorry, not this one. Scalar and scalar is going to be an equation involving beta 0 and beta 1. And I'm sorry, these are, of course, should be hat. Once we write an equation equating it to 0, then we have hats here. So this is going to be the second equation. So we have actually equation 1 here and equation 2 here. Simultaneous solution of these equation will give us these beta 0 hat and beta 1 hat values. Note that they are going to be estimates. These are very much like x bar s square, right? The solution to those equations. They are not mu and sigma square. So these betas are under relation of, so beta 0, beta 1 looks like these, whereas beta 0 and beta 1 here. So the estimates, the ones with the hat looks like these, whereas the actual beta 0 and beta 1, which are going to be, for most cases, they are going to be all unknown. They are never going to be known, are going to be population parameters. The best that we can do is to estimate them using samples. All right. So, well, actually, you don't need to go over this procedure over again and again. If you go a couple of more steps, since these are all the parameters in these equations are only summation of xi values, yi values, or cross products of x and y values, we actually, as I'm going to skip these parts because they are total mathematical, it's just solution of two equations with two unknowns. We end up with these solutions. Basically, what we call beta 1 hat can be found as the ratio of sum of square of xy product and sum of square of x values. And what are these xy? Xy is actually equal to this one. Say sum of square of xy or sxy, whatever you like, what is equal to I1 to n. Each yi value subtracted from the sample mean. Note that y bar is going to be the sample mean of y, and each xi value is going to be subtracted from the sample mean, right? Then they are going to be multiplied with each other and added. Now, one interesting point, actually, this is reduced to this form, and this is a very nice and very simple proof for that. And I think at this level, you can very easily handle that. The idea is very simple. From I1 to n, we can write this as yi times xi minus x bar minus from I to n xi minus x bar. All right. Now, note that there is no index here, so we can take this out and write this as y bar I from 1 to n xi minus x bar. Now the question is, what is the sum of deviations from the mean? This is actually equal to 0. This is due to the definition of mean. If you don't believe me, let's also prove that this is the case. We can write this as xi minus I from 1 to n x bar. And this is going to be equal to n times, because it's a constant, so we sum x bar n times, so it's going to be n times x bar. And this is going to be equal to sum of all the values for xi, right? So this is going to be also equal to n x bar. Or if you still don't like, instead of x bar, we can write it here as n xi summed over n instead of this x bar value. N will cancel, and we are going to get end up with sum of summation of xi values. So if you subtract them, this is going to be 0. Therefore, this can be also written in this fashion. And note that one can also write it in other ways. What do I mean by that? We can also write it as xi yi minus y bar. You can also write it that way. So the result is going to be xi yi. I'm sorry. This is going to be the single term, and the term that we are going to omit will be minus x bar. Let me go skip one step, yi minus y bar. And note that due to the very same reasoning, this is going to be equal to 0. So this is going to be also equal to, can be represented by this equation. That may seem just like a detail, but it's a nice exercise. And also it's a good thing to remember that the sum of deviations from the sample mean is actually equal to 0 due to the definition of sample mean. Anyway, sum of square of x values is defined by this equation. So this equation, actually, this one is going to be calculated using this expression, and this sum of square of x values is going to be determined by this expression, and the ratio is going to be simply equal to beta 1 hat. And beta 0 hat is going to be calculated using y bar here minus this beta 1 value estimated here multiplied by x bar. Very simple. So now, once we have these values, let's put them here in the equation. Now, our original equation is this. Yi is equal to beta 0 plus beta 1 xi random error. Now, on the other hand, what we have right now is actually beta 0 hat plus, beta 1 hat xi. Note that this is a sample regression model using population parameters. Here, instead of these population parameters, we have their estimates. So when we add those, and note that we don't have any term related with this yet, we are going to talk about this variance in a couple of minutes. This is going to be equal to yxi or yi hat. So this is going to be, this quantity is going to be the point estimate of y at that specific xi value. So you may ask, what is this quantity? What's the meaning of this quantity? The predicted or the estimated value of y at xi. Actually, this is, note that without the error term, this corresponds to the equation is yi given at some xi is equal to beta 0 plus beta 1 xi. And now note that the equation that we have is pretty much similar to this form, yi or y, let's call, not use I here, y at xi hat is equal to beta 0 hat plus beta 1 xi hat. Therefore, what we have here as the estimate is actually equal to expected value of y xi. It is estimated value. So what we are estimating using these estimated parameters given some xi value is the estimated value of y response variable at that xi value. It's expected value, not a single observation, because single observation will also contain the random error term, and we would never be knowing what the random error terms are going to be equal to in the future. On the other hand, I can estimate the expected value. So if you run the experiments a sufficient number of times at that xi value, this is going to be the average y value that you are going to be obtaining. This is going to be the estimate of that average value. I may call it that way. Okay. Now comes the intricacy that I tried to talk about. I said that there is a slight abuse of notation. Now, about this part. Now, what is the quantity that we obtain if here, instead of beta 0 and beta 1, if you use beta 1 hat and beta 0 hat and beta 1 hat? What is the quantity that we obtain? It is what we call residuals. So the quantity that we obtain when we subtract the actual yi value from its predicted value. And note that this is actually equal to, again in parentheses, beta 0 hat plus beta 1 hat xi. This is not, at first sight, one may think that this is the error term, but it's not the error term, because in order to obtain the error term, we need the real beta 0 and beta 1 values. We will never know what the error term is going to be, but residual is going to be its estimate. So this is going to be an estimate of what we call residual, is to obtain an estimate for the error term. And here's an interesting point. Actually, what we did here is to minimize the residuals, because actually in this part, when you square it and take the derivative here, now once you take the derivative here and equate it to 0, what is written inside the parentheses is not now an error term, right? Because we solve the equation for the least square solutions, but it is called a residual. What does residual mean graphically? It is very easy. Actually, it is what you may think an error to be equal to. Well, actually, once let's say that we have these values here. then what you can do is you may draw this line, this beta 0 at beta 1 xi value, because this is actually in from a graphical perspective, this is the equation of a straight line. All right, now what does this straight line first correspond to? This is going to be estimate of expected value of y given xi. So again, let's see, this is, note that, all right, this line here is the expected value of y given xi. Given xi, what do you expect xi to be equal to? This is the true line, right? The true relation. But given some data, when we estimate this relation using beta 0 and beta 1 parameter estimates, then what you can obtain at most is not this one, but the estimate of that one. So when given data, this empirical line, I may say, is going to be the estimate of the expected value of y given some value of x. All right, since this is the estimate, now note that the distance or the difference between the actual observation and this point here, the difference is not going to be error, but what we call residual. If instead of this one, if we had known the true values of beta 0 and beta 1, and if we plotted these, right, then this line, the difference between the actual point, observational point, and the true value, true expected value, would have been error. That's why it is here, this difference is error 1, if you call it x1 here. Whereas in the other graph here, in the other figure, since this line is drawn using the estimated values of beta 0 and beta 1, these are called residual 1, residual 2, things like that. So again, here, the very same, let me say, the abuse of notation. Don't be go into that much details, but for the curious souls, maybe who may find a contradiction here, note that actually what we are trying to do here is not to minimize the error values, because we don't know these errors, but given some parameter estimates, we have the corresponding residuals. So actually these are the residual values. So there's that slight but subtle point, and it is of course statistically important, but in your level, just keep that in somewhere in your mind, but don't take it of too much concern, I may say. Anyway, so actually we can find the residuals using this very simple equation, because we know the beta 0 and beta 1 hat values for each xi. You calculate its estimate of the expected value, or yi estimated value, and the difference from the actual yi is going to be the residual. Now comes the equation for determining the variance estimate. What we call sum of square of residuals, unfortunately this is a misnomer, or this is maybe a little misleading, but this is used in your textbook. This is what we call sum of square of residuals, right? Is defined by the square of residual terms. Is going to be this. When you divide it by n-2, you obtain a population variance estimate. Actually, this is going to be the variance estimate of the estimate of the variance of the noise. Now, this probably looks like many other things that we have covered. For instance, what we call S square is y minus my y bar square and minus 1. All right, it should suspiciously looks like this one, but this is far from, you may say that it's far from y bar. Actually, y bar, let's recall, y bar is an estimate for, if you have, it's the sample mean, is an estimate for population mean. And what was the model for this single variable case that we have used? I said earlier, y is equal to mu plus error, or as the sample model is going to be yi is going to be mu ei. So this is actually the expected value of yi, right? So actually this is going to be an estimate of y, because since this is actually an this is equal to the estimate of mu, and since expected value of yi is equal to mu, therefore this quantity here, when we actually would like to predict, use prediction both sides, this is expected value of yi predicted. So y bar is exactly expected of y bar I, its predicted value here. So the very same thing occurs here. The predicted value. By the way, there is, I think I should say, instead of prediction, because prediction is usually reserved for future values, I may say I should have said estimated, or even better, fitted value. Here is going to be a better, I think, phrase to use. Anyway, so this is the fitted or the estimated value for YR. This is going to be expected value, YI estimate. So the very same thing here. So what we have done here is S square is equal to yi minus estimated value of yi, right? Expected value, square root of n minus 1. Why n minus 1? Because we obtain this quantity also from the data. And during that, we lose 1 degrees of freedom. So the very same thing applies here. This is actually equal to, note that this is yi minus this quantity is expected value of yi given xi, y, but it is estimated value. We square this, the very same thing, divide by n minus 2. Why 2? Because in evaluating this expression, we have already used the whole y values and xi values together to come up with beta 0 and beta 1 hat. For this case, we have already used this data to come up with y hat. We lost 1 degrees of freedom, we now lose 2 degrees of freedom. The very same logic applies. Of course, the derivation is a little bit more involved of this this quantity, but nevertheless, the idea is still the same. So these three things are going to be our estimators. So what do I mean by that? These three quantities, beta 1 hat is going to be found by this expression, beta 0 hat is going to be found this expression, and sigma square hat is going to be found by this expression. Now I'm going to continue with applying the same treatment that we have employed on the estimators that we have used up to this point. Now that we have our least square estimators of beta 0 hat and beta 1 hat, now this part is given without proof, but expected value of beta 0 is actually equal to the true value of beta 0, and expected value of beta 1 hat, of course I'm talking about, is equal to the actual value of beta 1. Therefore, both beta 0 hat least square and beta 1 hat least square are unbiased estimators. So that is the first property that we need to remember. And then I'm going to find the variance of beta 0 hat, and then variance of beta 1 hat. But then actually I'm going to again give the results without proof. And these are equal to variance of error times this term. And now that, let's remember what, for instance, the variance of this estimator was equal to. Actually, if you compare it, variance of beta 0 with variance of beta 0 hat with variance of x bar, you can see that they are somewhat similar. We have, of course, this random error variance term, because if the variance of the random error is higher, then the uncertainty in parameter estimates will be automatically higher. So this is going to be, the first term is the identical term. The second term is the contribution due to the linear regression, least square solution of the linear regression problem. It is x bar. X bar is the sample mean of the x values in our sample and sum of square of x values, and this squared value. And variance of beta 1 hat, and remember, let's beta 1 and beta 0, what are these? Beta 1 is the slope here, whereas beta 0 is the intercept. So beta 0 hat is the estimate of the intercept, whereas beta 1 hat is the intercept of the slope. So intercept of the slope is equal to, again, it's proportional to the variance of random error, and this is divided by sum of square of x values. Now, At this very point, we should realize that beta 0 hat and beta 1 hat are both normal distributed. Why did I call it note that? Is it so obvious? Actually, it's pretty much obvious. If we go back, now here beta 1, as you can see, is a function of, and actually a linear function of, yi values. Now this is equal to, I write here, yi times xi minus x bar. Note that these are fixed values by the experimenter. So the random variable here is yi. This is going to be divided by then xi minus x bar square values. Again, these are fixed values. So therefore, this is going to be just a linear combination of each y1 to yn values. So what about these? Each of these values are actually conditionally normal distributed, and they are conditioned on the x values. So this is going to be equal to beta 0 plus beta 1 x1 with the sigma square standard deviation. Y2 is going to be normal distributed with beta 0 plus beta 1 x2 with this variance, noise variance term. So all of these y terms are normal distributed, since the random element, random variable that affects these y to be, that causes these y to be random variables, is the noise itself. So it is the noise of the variance that is in action that makes this a statistical term. Anyway, so we have a summation of normal terms. And since we have a linear function of normal variables, then the resulting variable, random variable, is still going to be normal. So it's the very same thing here. So both beta 1 hat and beta 0 hat will be normal distributed. That's one important point. Therefore, now we have all the information that we need here. So beta 0 hat is going to be normal distributed with its expected value equal to beta 0. And the variance is going to be equal to this. I'm not going to write this again. And beta 1 hat is going to be normal distributed again around the expected value of beta 1 hat, which is equal to beta 1 itself, its real value, and with its corresponding variance term here. Note that this is very much like x bar, which is normal distributed around the population mean, and this is the estimate of the x bar. So it's the population mean which is estimated by x bar, and the variance is equal to sigma square over n. So the very same thing here. This is an expected value of x bar is equal to mu unbiased estimate or estimator of population mean, unbiased estimators of beta 0 and beta 1. Therefore, least square estimators carry a similar role to x bar. Actually, I don't want to go into that much detail, but x bar itself is actually without including the x term. So let me put, instead of x bar, let me put y bar to denote it, to denote that we are dealing with the response variable. So if you have different y values here, y to n, then if you apply the least square approach, which I'm not, maybe I'm going to leave it to a bonus video because it's something interesting, but very simple actually, then the least square is not going to be a line here because they are all on a fixed single x value. You may think of, actually I talked about that in the previous lecture. There is no change in the regressor, so it's just the model is, for that reason y I is equal to beta 0. You can call the model something like this, plus error 1. The estimate of here, beta 0, the least square estimate is going to be equal to x bar. So that might seem an interesting point. Again, y bar, sorry, y bar. So sample mean without inclusion any regressor effects is going to be the least square estimate for the parameter of beta 0 in this model. So it's not something, that's why there's a continuum between what we have covered up to this point. We haven't maybe used statistical models, right? In this form, we haven't used least squares, but actually you can obtain the very same results using a statistical model, and the parameter estimation by least square give you identical results. Okay, so whatever we have encountered previously in terms of the problems about having information about sigma, we are going to have the same thing here. Note that we previously talked about in populations where sigma square is known, then we can directly use standard normal distribution. That's nice, but usually we won't be knowing the variance of the random error or the noise term. So what we are going to do is, instead of this variance, we are going to be use its estimator. And estimator is going to be, as you can see, is given by this function. Sum of square of residuals computed by this approach, right, divided by n minus 2 is going to give an estimate for the variance of residuals. So when you take the square root of this quantity, you are going to be estimating standard deviation of random error terms. So anyway, so in this case, estimated standard error terms for beta 0 and beta 1 is going to be equal to this estimated standard deviation term, and multiplied by product square root of these terms, and same thing for beta 1. So in this case, when we use estimated standard errors instead of the actual standard errors, that is, instead of the variance terms, we don't know these, if we use their estimated values, then the resulting distribution, when we normalize the quantity, is not going to be normal distribution, but it's going to be t-distribution. Actually, we devoted a couple of lectures to that topic alone. So that was maybe basically one of the building blocks of this course. So I'm going to be using the t-distribution or the t-distributedness property of the parameters in the next topic, hypothesis test in simple linear regression. Now, when we were dealing with single random variable cases, we were dealing with population mean, sigma square, all these things. And the hypothesis tests were like mu is equal to some value, mu is not equal to some value. Now we were talking about maybe two different populations, then mu1 is equal to mu2, mu1 is greater than mu2, kind of thing. Now, you can write the very simple, very similar hypothesis test also for beta 1 and beta 0. Note that now these are the population parameters that we have. But with respect to those hypothesis tests you can write, there is actually a special one among all the possible an infinite number of hypotheses that you write. It is this one. What is so special about this hypothesis test? Now, corresponding to this test, again, remember our single variable model. When we actually do a hypothesis test like this, is not, well, there may be some special meaning to that hypothesis test, but usually 0 is like any other value. You could have tested this equal to 10, or you could have tested this equal to 100, or you could have tested equal to 0. Why does that carry a special significance when it comes to this parameter? And note that it's not beta 0, it's beta 1. It is this. Now note that the relation that we are trying to find is between an independent variable and a dependent variable, between a predictor or a covariate and a response variable. On process engineering terms, this is actually a process or even manipulated variable. I think this is the best way to understand from a chemical engineering perspective. And this is going to be the response variable, or call it quality variable. So your manipulated variable, maybe you have a process here. I think you are accustomed to seeing these kind of rectangular processes from a material energy balance course. So there is an inlet or input to that process, and there's a certain output. And I'm interested in that some property of this output. It may be anything, viscosity and refractive index, concentration, whatever. And that inlet may be, for instance, flow rate or temperature of the inlet, or raw material, some properties of raw material, whatever. Now call this U1, the manipulated variable, the inlet property. Let's say that you can change this. If this is, for instance, flow rate, you can easily change it. If this is temperature, yes, you can change it through passing through a heat exchanger, which you are going to cover in this term in your heat transfer course. And the output variable is going to be composition. So based on this, and note that we are talking about a single variable here. In real life, we have many of these variables, but since we are talking about simple linear regression, we have to confine the whole topic all the whole issue, unfortunately, to a single regressor. Anyway, so what we would like to understand is, when you change this U1 value, does it affect C or not? So is there a causal relation between those two? And to test these kind of hypotheses, there are certain design of experiments constructed, which I'm not going to go into. But let's say that you have designed your experiment in this way, and at certain U values, you have performed the experiments. And these are the results. Now, from these results, of course, in reality, you may be performing more than 4 experiments, but I'm just going to, okay, let's put another one. Now, from these, you can always come up with a least squares fit here. This is going to be, let's say, it's going to be something like this. Now, the question is this. Always, there is going to be a line like this. And this line is going to have these parameters, beta 0 here, intercept. Note that it's the estimated value, and there's going to be a slope value here, beta 1 hat. Beta 1 hat is never going to be equal to exactly 0. Why? Because beta 1 hat is a real number, and unless you take a very limited number of significant figures, this figure, and in reality, in mathematical, from a theoretical perspective, if you take infinite significant figures, from whichever sample that you measured or that you compute the beta 1 hat value using least square analysis, this is going to be always non-equal to 0. However, here let's talk about 2 different issues. One of them is that U1 really affects C. And the other scenario is actually there is no relation between U1 and C. Now, how can we test whether no relation case exists or not? This case is going to reflect itself in this model. Y is going to be equal to some beta 0 value may be there, but it's going to be 0 times X and a random error. In real life, due to this random error and due to other factors, right, which are going to be affecting the system, I have talked about this, the meaning of beta 0 previously. This Y is going to be, first of all, non-zero, and even if you repeat the experiment for different or the same X values or different X values, it doesn't matter. Y will be changing from experiment to experiment. So since Y will be changing from experiment to experiment, you may think you are going to always, even that if this is the case, you may easily observe or obtain a data such as this one. Now, this data for the inexperienced eye, one may think that depending on, let's say, these are the number of experiments or X1 values that we have used, since X does not have an effect, it's going to be multiplied by 0 here. For whichever value of X you use, it's going to be 0. So we expect Y to be fluctuating around a single beta 0 value. Let me use a different color pen here. All right. So this is, in reality, there is a constant beta 0 value here. Note that I do not put here now a hat. This is the reality that we would never know. Remember the case I talked about in hypothesis test, what we know, and there is that guy who knows the ultimate truth and the communication between those two. The guy who knows the ultimate truth can find the type 1 error, type 2, the type 2 error, all these stuff, because he knows the ultimate truth. But in reality, we wouldn't be knowing beta 0 value. But what I would like to say is that in reality, we would be obtaining around some beta 0 value with some fluctuations. Now, let's say that these are the fluctuations are like this. Now, when I erase this, because in reality, this is what I observe, I'm going to be obtaining these values. And note that for these values, it's going to be always possible to fit a line, right? A least square line, and this least square line is never going to have a beta 0 value equal to 0 due to the reason I explained. So it's going to be either like this, right, or it's going to be like this, depending on the significance that you obtain. Well, actually, also, by the way, note that let's obtain that a value like this, beta 1 is equal to 0.01. You cannot call this value to be a small value because this is all unit dependent. What do I mean by that? Let's go back to this equation. Now I'm going to write this equation with its units. So let's write the unit of y. Just let me, let's talk about this case here. Here concentration is y, and it's going to be, let's say, moles per liters. And this U1 is, let's say, the temperature or flow rate. Then this is going to be liquid liters per second. So this is the input variable, this is the output variable. So if you write the relation between them, this is the relation at hand, moles per liter. Beta 0 should be also moles per liter. Of course, its estimate also should be equal to moles per liter plus, I'm sorry, get rid of this, plus beta 1 times x. X is liters per second. Therefore, beta 1 should be such that when you multiply by this one, you are going to be obtaining this value. So it's going to be, I think there should be also a mole here. Mole times second times the liter square. When we multiply those, seconds will cancel, right? I'm going to have moles per liter. All right. So the 0.01 value that you estimate has the units of mole multiplied by second per liter square. If this the unit conversion that I've done is right, correct. Well, it doesn't matter much whether it's correct or not, because the idea is here, I guess. So what I'm trying to say is that you can easily change this. For instance, if you use millimoles, you are going to be multiplying by 10 to the power 3. If you change it to micromoles, if you would like this to be micromoles, then this is going to be equal to this quantity multiplied by 10 to the power 6. Then it's going to be equal to 10 to the power 4. So now our beta 1 value seems to be huge. So a single value, right, does not mean anything because it's all unit dependent. So we cannot easily say whether the beta 1 hat value that we find is close to 0 or not, because it's unit dependent. So what I'm trying to say is that we have a serious problem here to check whether there is actually a relation between x and y, or there is no relation between x and y, but beta 1 is come out to be equal to non-zero due to only sampling variance. And for this part, to be able to test this test is called significance of regression test. Note that in this case, beta 1 cannot be equal to any other value. Beta 1 is equal to 0 will correspond to no relation, or significant, or regression is not significant case. On the other hand, this case will beta, the alternative hypothesis will refer to relation between x and y. So in your test, when your t value that we are going to be calculating, when it's found to be extreme, then we are going to say that beta 1 is not likely to be equal to 0. And that means there's going to be a relation between x and y, because slope is the thing which transmits the effect of x to y. Think about like that. X, a change in delta x transmitted to a change in delta y, right, through the slope. So if this is 0, it means that delta x will have no effect on changing the y value, so there is no relation. And on the other hand, if the t value that we calculate will fall in the limits, then we are going to say that, again, we cannot say that we prove or we show that there is no relation, but we are going to say that there is not sufficient evidence to suggest that the regression between x and y is significant. So again, it's not going to be an acceptance of the null hypothesis, but not being able to reject the null hypothesis. So what's the test statistic that we use? It's going to be t0 value. It's the very same thing we have employed previously. When it was x bar, it was x bar minus mu0, and mu0 came from the non-hypothesized value here, right? Whatever the alternative y was, divided by standard error of x bar, and that was actually equal to standard error of x bar was equal to standard deviation, sample standard deviation, square root of n. So we are going to be using the very same thing here. Instead of x bar, we're using the parameter estimate of beta 1 hat. beta 1 0, actually this is the expected value here, right? So beta 1, and the expected value here, assuming that null hypothesis is correct, we put it here, just like we use mu 0 here. And we divide this by a standard error term, this one. And this is going to be again found from the residues. So if your T0 value is greater than T alpha over 2, please be careful with degrees of freedom about the t-test. Is this t-test, this is, if the null hypothesis is correct, this would be a t distributed with n minus 1 degrees of freedom. Now this is t distributed with n minus 2 degrees of freedom. And I explained where that additional degree of freedom, the loss of that additional degrees of freedom. All right, now, what about the confidence intervals? It's going to be the same thing that we have covered previously. So I'm just going to give you the result. Beta 1 is going to be between those two limits with a probability of 100 times 1 minus alpha percentage, and beta 0 are going to be between those two limits. How did we find this? These are the point estimates of beta 1 here. We add and subtract the same value, which is the standard error term here, and the corresponding t distribution values, and the very same thing for beta 0. So there's a very straightforward procedure. Now, one thing that you can actually, if you like, of course, if you are interested in a certain property, you can also do a test like this. Beta 1 is equal to 0, beta 1 is not equal to 0 or greater than 0. So if this is the test that you apply, then instead of this beta 0, of course, you are going to be putting this value. But note that this is going to be a specific test. It's going to be a test that the effect of x on y, the magnitude is equal to 10, whatever the units is equal to. This is going to be a test which is going to answer only that specific question. Even if you don't have that specific question, you should always conduct this test, because as I said, this test has a special meaning when it comes to beta 1 is equal to 0. And there is no counterpart of this test in terms of beta 0. You can do this test, but again, this is going to be specific for your purpose. You are, for some reason, interested that beta 0 is equal to 0 or not. There is nothing that no relation of this test to the significance of regression, because what we are trying to find in the significance of regression is the relation between x and y. Whether it intercepts here or anywhere, or it's 0, whether it's here or it's here. Okay, so any of these, for both, if these are the true lines, there are the x and y, the relation is significant. The relation between those two variables is significant. So whether beta 0 is 0 or not has got nothing to do with this idea. On the other hand, if the regression line is the true regression line is this one, then we can say that x and x does not affect y. This is the issue here. The last thing before continuing with an example I would like to talk about is the confidence interval on the mean response. Now, let me talk about the motivation for the confidence interval for mean response. What do I mean by that? Why do we have another confidence interval? Because up to this point, we had confidence interval for population parameters. And here are the population parameters. And shouldn't that be all? Actually, there is a subtle difference here. Previously, note that in a statistical model form, that was the type of equation, or that was the type of statistical model that we were dealing with. And we came up with an estimate of mu, and that estimate of mu was done using x bar, and using x bar, we came up with a lower and upper confidence limit for mu value. That was equal to 1 minus alpha kind of case. And we conducted hypothesis tests on this mu. Now, I said that mu is like beta 0 and beta 1, but on the other hand, we can exactly find another term which is much more similar to mu. Note that this mu is actually equal to expected value of y. And x bar is, as I said previously, mu hat which is equal to expected value of y hat. Now, when it comes to regression, actually the expected value, let's again remember the regression equation, beta 0 plus beta 1 x plus I. Now, the expected value of y given xi is going to be equal to beta 0 plus beta 1 xi. Note that this new quantity, this quantity, expected value quantity, contains both beta 0 parameter and beta 1 parameter. So you can also show it like that if you like, to make it easier to maybe to grasp the idea. This is mu y given xi, similar to mu here, mu value here, right? Or this expected value. And when we find beta 0 and when we determine beta 0 and beta 1 by least square estimates, therefore, what we determine is expected value of yi given, or expected value of y given xi hat is going to be equal to beta 0 hat plus beta 1 hat xi. So what I'm trying to say is that I note that is equal to, again, in another form of showing, mu y given xi hat. We are using this to estimate this quantity. And therefore, this note that this is a population parameter. Given xi, mu expected value of y is going to be equal to a constant. Therefore, we can find a confidence interval, a lower and upper confidence interval for this quantity. And note that this is going to be an additional one, but this quantity will actually be the most similar one to what we have covered previously in terms of population parameter mu. So population parameter mu, you may think about it that way, will depend on the xi value, but also will depend on beta 0 and beta 1. So given an xi value and the beta 0 and beta 1 hat values, then we can determine, we should be able to determine a confidence bound or confidence region such as this one. Therefore, this is what it says, confidence interval on the mean response. The mean response, I repeat again, is actually equal to mean value of y given xi. Actually, note that this is equal to that line that we have here. This is the true value here. This is true regression line. On the other hand, let me again use another color here. And I'm sure there is an easier way for that because it takes a bit of time. Anyway, and this is going to be that line, the true regression line. On the other hand, this may be, for instance, given a sample values, this may be one of those mu y given xi at values. This may be another of those estimates depending on the sample. It is very much like having, for instance, okay, let me not draw the y-axis, it's going to be only the x-axis here. If this is mu y, our x bar value here falls here, another x bar value falls here. Each of these sample means, which are estimates of these, which are an estimate of mu y value, falls on the left hand, on the right hand side. Actually, we have a normal distribution here, sampling distribution we call it. It's the same thing here. We have a sampling distribution of mu y given xi hat values. So we are going to have all these, depending on different samples, we are going to have, of course, if you have a very small sample size, the deviation is going to be smaller. If you have a large sample size, the deviation is going to be, I'm sorry, if you have a small sample size, deviation is going to be larger. Actually, you can easily see it from here. Variance of beta 0 hat is actually dependent on n value. If n is small, if you take, for instance, only 5 observations, and from those 5 observations, you would like to try to obtain a regression line such as this one, and that would be equal to expected value of y given x hat, or mu y x hat, or y x hat. This is going to have a high variance. And it is exactly this quantity that we would like to, using this quantity, we would like to determine the confidence interval of the mean response, which is equal to that one. Anyway, so what we need actually is the variance of this quantity. And the variance of this quantity is actually very easy to calculate. It's going to be basically equal to variance of expected value of y given x0 hat. And since this is equal to that quantity, I can directly write it here. Now, this is going to be equal to variance of beta 0 hat plus x0 square variance of beta 1 hat, because x0 square is a constant. Now, the confusing part, I'm not going to go into that detail because the derivation is out of the scope of this course, is we are going to have also an element of 2x square covariance of beta 0 hat and beta 1 hat. Now, I just would like to mention that this is a bit of out of the scope of this course, yet still for the curious souls that may be interesting. Now, you should ask this question. Is the estimate of beta 0 intercept, is the estimate of slope, are they correlated with each other? Yes, they are. That's an interesting thing, and it's very easy to see only by a visual or visual inspection of heuristics. Think about, let's say we have a sample like that. It may be, for instance, a line such as this one. If you had another observation here, then that line would have been something like this. Now, note the very interesting thing. As the slope estimate increases, the intercept estimate will decrease. So covariance between beta 0 and beta 1 is going to have a negative sign. Its correlation is 0. So we have to derive this, which is out of the scope of this course. Anyway, when you actually derive the result is going to be equal to this. As you can see, it somehow takes this one and takes this one, and of course, taking also the correlation into consideration, you end up with this equation. And the very same logic applies here, since this statistic is a linear combination of two normal distributed statistics. Note that beta 0 and beta 1 are both normal distributed random variables, right? Therefore, this is going to be also normal distributed. So this one, and the expected value here is going to be equal to the expected value of, actually that's an interesting quantity, expected value of the predicted value of this one, or the estimated value of this one, is going to be equal to expected value of y x0, which is the true parameter value. So this quantity will be normal distributed around this value, the true parameter value, and with this variance. Put the variance here, and this is going to be what expected by x0 at. So this is how this statistic is distributed. Therefore, since we don't know the sigma square, instead we use sigma hat here. Therefore, this is going to be t distributed, and we can find the corresponding confidence interval here. But here the meaning is more maybe important. We find now a confidence interval not for beta 0 and beta 1. We find a confidence interval for the line itself, which is the expected value of y given x0.